Chinese metro line runs straight through floors 6 to 8 of a 19-story residential apartment building. That's only the visible tip of a 50,000 kilometer production system most people will never get to see. Steel, track, viaducts, tunnels, and maintenance, all running as one moving factory. We're walking through how it really works, and stick around to see how a bullet train takes a shower. Most countries build railways. China does something else entirely. They rebuild railways while passengers are still traveling on them. One night in Fujian province, 1,500 workers, 23 excavators, and 7 freight trains connected a brand new high-speed line with 3 already existing ones, start to finish in just 8.5 hours. You read that right. The Chongqing Metro runs through floors 6 to 8 of a 19-story apartment. Rebuilding a line in 8.5 hours is one feat. Producing thousands of kilometers of new line at industrial pace is another problem entirely. And that's where China rewrote the playbook. Long before high-speed rail at Chinese scale, European contractors had already turned track laying into mechanized production. The standard runs cleanly. 2,000 sleepers delivered per day. Exactly 1,666 sleepers per kilometer. Pusher wagons installing continuous welded rail in 404 metro sections, fast clip fastenings, joining, and final clipping. China studied this entire sequence, then scaled it, most visibly by jumping from 404 metra to 500 metra rail sections laid in one continuous pass. In Western Europe, the RU-800S work train and the PM-1000 URM ballast cleaner already turned track renewal into one moving operation. A single machine train rips up old rail, screens or replaces ballast, lowers new concrete sleepers at preset spacing, and pneumatic torque wrenches drive the clips home, all in one slow, continuous pass through the entire worksite. The European model proves the principle. Rail construction works best as a moving factory rolling itself forward. What China changed wasn't the principle itself. China changed the volume that principle had to handle every single working day on the network. Italian railway renewal follows a similar operational logic, using specialized equipment and a fully structured step sequence. Crews remove the old fastenings. Renewal equipment extracts worn sleepers and installs new ones in a continuous operation. New clips are driven into place. Aluminothermic welding fuses the rail joints. A magnetic sweeper collects iron scrap left along the track. Ballast regulators reshape the ballast profile. Tamping equipment restores track level and alignment. Ballast cleaning and renewal systems replace the entire ballast layer and install a non-woven insulating fabric beneath the track structure. A final tamping pass completes the geometry correction before the line returns to service. Every step has its own specialized vehicle. We're looking at roughly 10 distinct machines collaborating on a single stretch of track at any given time. Now picture that same logic, spread across a country building tens of thousands of kilometers of high-speed rail across 2 decades of continuous construction. That's the actual scaling leap China made on its own. This is where the volume kicks in. China's high-speed track laying centers on something that sounds impossible until you see it. Rail segments 500 meters long, transported on dedicated trains and laid down in one continuous motion. The starting point is the rail yard. Standard rail bars weld together inside the production facility into single 500-meter runs, 5 times longer than the 100-meter segments most countries treat as standard. Loading those onto a transport train requires a specialized flatbed convoy supporting the rail along its full length. The train then runs directly to the construction site, where a ballastless track bed has been prepared in advance. Ballastless construction is the second leap. Concrete slabs cast to millimeter tolerance replace the gravel ballast used in conventional lines. The slabs lock the track geometry in for the life of the line and eliminate the regular tamping maintenance that conventional ballasted track demands. The track laying machine then takes over. A specialized rail laying vehicle grips the lead end of the 500 matcha rail, pulls it off the transport train, and guides it down onto the prepared concrete bed in one continuous draw. 500 meters of seamless steel, laid in one single pass. Workers follow behind to anchor the rail with bolts and elastic fastening clips. How do you join 500 meter segments cleanly enough for 350 kilometers/h running? Aluminothermic welding for the field joints, followed by precision grinding to flatten the weld, followed by ultrasonic testing to confirm zero internal flaws. Every joint becomes invisible to the train. The result is what railway engineers call seamless rail. Kilometers of continuous steel with no perceptible joints. At 350 kilometers/h, every joint you remove is one fewer vibration, one less weld point to crack, one more decade of service life on the rail itself. The Taklamakan Desert Loop carries the same machine-led production across 825 kilometers, with more than 630 of those through pure sand alone. 50 million square meters of grass net cover and 12.96 million planted trees stabilize the line. The desert threatened to cover the railway with sand. The railway was laid faster. At the opposite extreme, the Mudanjiang-Jiamusi line runs through northeastern winters that drop to minus 35 degrees Celsius. That mechanized installation approach also operates in cold conditions thick enough to crack standard fasteners outright. Track laid this fast still needs the right thing underneath it. That's where slab track quietly takes over the story. A 500 meter rail laid in one motion still needs the right foundation underneath. That's where slab track comes in, and most riders never realize how much it determines. In Nottingham, a tram extension uses the Apitrack system, track bed preparation, concrete poured onto reinforced foundations, large pavers smoothing with surveying tools, then anchor blocks set down the center line. Crews clamp the rail segments. Thermal welding fuses joints. Excess metal grinds off. The principle, lock the geometry into the slab, not into the ballast. Maintenance drops dramatically. This same idea, scaled and refined, is what China's high-speed network rides on. The Rita 2000 system, developed in Germany, is the template. A first concrete layer goes down on the prepared platform. 2 concrete pavers feeding internally vibrated concrete produce about 400 meters of single track per day. Reinforcement mesh drops on top, followed by bi-block sleepers precisely leveled before they get embedded into the layer below. The sleepers fix to 25 meter rail segments to hold position. A second concrete layer pours around them, vibrates, and levels into a solid slab. If you've ridden a Chinese high-speed train and noticed how little vibration reaches your seat, this is what's underneath you. Slab track is what trains touch. What carries the slab matters even more. And on a network designed for 350 kilometers/h, the answer is bridges, almost everywhere along the line. In Paris, the 1868 Viaduct de Souverains was refurbished in a 300-hour campaign. Track stripped, old vault structure demolished, prefabricated concrete deck modules craned in by a custom-built rig, ballast and rail relayed, joints welded, overhead wire restored. The takeaway is straightforward. Prefabrication compresses time enormously. China took that concept and scaled it beyond one bridge, deploying it across tens of thousands of spans throughout the network. Zurich tells a related story at urban scale. The Bellevue Tram Junction handles 75,000 transfers and 60,000 vehicle crossings every day. Then, for a brief period, everything stopped. Crews replaced 1,750 meters of track, 19 switches, 3 lubrication units, and 4 rail expansion joints before traffic returned. The numbers behind the work: 3,500 cubic meters of demolition removed, 800 cubic meters of recycled gravel laid, 1,600 cubic meters of concrete poured. Over 400 workers staffed the first weekend, working through the night under floodlights. The Bellevue rebuild ran as a perfectly organized machine. Partial demolition at one end of the site, reconstruction already starting at the other. Welding ran mostly at night. 73 components fused on the first weekend alone. Buried infrastructure forced surgical demolition, since some old utilities ran higher than the original drawings expected. The principle that made it work: stage everything, parallelize everything, sequence handoffs to the minute, and refuse to let one single delay cascade into the next stage of work. You can see the family resemblance to what China later turned into national policy across the whole country. Precast everything. Schedule overlapping crews. The actual difference is volume. Zurich rebuilt one junction in roughly 8 weeks of intense work. China extends this same level of organization across tens of thousands of kilometers of new viaduct, every year, on dozens of independent sites simultaneously. The choreography is similar. The map is on a different scale. China's working method for high-speed viaducts is precast box girders, each one weighing up to 1,000 tons per single span. A gantry crane lifts the girder from the casting yard. A multi-axle transporter carries it along the already completed viaduct deck. The transporter rolls into the frame of a bridge erecting machine perched at the leading edge of the line. The machine takes the girder, slides forward, and lowers it onto the next 2 piers. So why build viaducts at all instead of standard embankments? Bridges occupy a fraction of the ground footprint, vital in densely populated regions. The factory side feeds the field side directly. Inside the casting yard, reinforcing steel gets bent, framed, and digitally tracked through 9 stages and 18 procedures. Operators monitor every single cure on smartphones in real time as it happens. Each box girder cures over 42 days under automated water spraying, then accepts post-tensioning cables threaded through internal ducts. The finished 1,000-ton girder gets sealed, surface protected against wind erosion, water intrusion, extreme heat, and extreme cold, then craned into storage. Bolted into place on site, each girder becomes one more span. Pier by pier, the viaduct advances at production pace. When viaducts aren't enough, the network goes higher still. In Wuhan, a suspended monorail glides above traffic at 60 km/h, and above the city is one direction. Through the mountain is the other. When viaducts hit terrain, they can't span. The network goes underground. China drills rather than detour. European rail upgrades often shift entire alignments instead. In Paris, the RER-B line was displaced 1 kilometer to free space for a new TGV route. Every meter of track, every overhead mast, every foundation rebuilt onto a new corridor. Soil from the dig got reused on site, cutting earthworks from 3 weeks to 1.5. Let's see how Germany applies those standards in tunnel construction. The Rastatt Tunnel on the Karlsruhe-Basel line is a fully ballastless installation built on the Rita 2000 system. The numbers tell the scale. More than 12,000 precast concrete cover slabs installed, around 100,000 cubic meters of concrete poured, 2,000 tons of reinforcement, roughly 12,000 meters of slab track across the bores and rescue gallery. Bi-block sleepers arrive precast for precision. Long welded rails arrive by train at an in-tunnel assembly bay, where 120 metro sections get bolted onto 180 sleepers and clipped tight. A specialized installation train, 10 bogies, 10 hydraulic track lifters, carries each section into the tunnel, lifts it into position, lowers it onto the floor, and bolts it to the prior section. Production rate, 360 meters per shift. After positioning, millimeter precision alignment uses spindles to suspend the rail while specialists fine-tune the geometry. Concrete pours around the sleepers to lock position. Beneath residential areas, a mass spring system isolates the rail from the tunnel floor, decoupling mats, elastic rubber, a heavy concrete mass plate, so vibrations don't reach the homes above. This is the level of precision China studied. China kept the precision and pushed the scale further. The decking tunnel on the Guiyang-Nanning line runs 6.61 kilometers straight through karst country. Imagine hitting one underground cave every 50 meters of progress. Engineers handled over 200 of them. 2 kilometers of the route passed through soft clay. The solution was 1,000 plus reinforced concrete piles and load-spreading rafts. Even within a single city, the challenge takes a different form. Chengdu Metro Line 6 runs 68.4 kilometers almost entirely underground, described as the longest fully underground metro line in western China. Shield machines crawled through clay and gravel beneath the streets. Tunnels solve geography. What runs through them is next. Before any railway exists, the metal has to come from somewhere first. A ground-level mold receives molten iron at around 1,300 degrees Celsius. 2 overhead cranes coordinate the ladles. One pours, the second waits loaded as a backup, so the stream never breaks mid-pour. Stop the flow for a few seconds, and the casting cools unevenly, splits during shrinkage, and weeks of preparation hit the scrap pile. Sparks fly from riser holes as displaced air escapes. The pit glows for hours afterwards, cooling slowly so the crystal structure forms uniformly across every cross-section of the part. Casting is one stage. Cleaning the steel itself is another stage. After primary melting in an electric arc furnace, liquid steel transfers to a refining ladle. The tap stream throws molten metal in a controlled arc. Refining removes inclusions that would otherwise turn into rail-cracking defects under cyclic train load. A slab is one shape. Getting it from a brick form into rail-grade stock is the harder question. Out of a reheat furnace, the slab glides at orange heat onto powered rollers. High-pressure water sprays blast away the oxide scale before it can press into the metal surface. Then comes the reduction sequence. Pass after pass, each stand squeezes thickness down and length up further. The longer the slab gets, the faster it has to move, and synchronization tightens to milliseconds. A finished strip leaves the line as coils, still warm enough to feel from several meters away. Length is leverage. Fewer joints mean fewer potential failure points. Modern rail mills can roll rails up to 120 meters long, allowing track to be installed in longer continuous sections with lower maintenance requirements. Even after rolling, a rail isn't ready to ship. It needs further reconditioning in a workshop first. A workshop shows the sequence. A milling head cuts the surface clean. An automated welder lays a fresh metal layer on the damaged crown, hidden under granular flux to keep the arc stable. a cupstone grinder takes the weld bead down to rough profile. A hand grinder finishes the contour. Get the grind wrong by 0.5 millimeter and wheel rail contact shifts enough to wear the head out fast. A laser-guided hydraulic bender then sets the camber to the exact installation curve. This is where the similarities end, and a very different scale comes into focus. China runs 7 specialized railworks for the national high-speed network, but the universal rail technology behind closed-tolerance rolling is engineered through a single integrated plant solution. Baotou Iron and Steel in Inner Mongolia has run this plant day and night for over 12 years. 8 million tons from one mill alone, feeding 50,000 kilometers of track. The slab leaves the walking beam furnace at 1,250 degrees Celsius. It passes through a 250-bar descaling jet before entering the first reversing stand. 2 breakdown mills reduce the bloom in stages, with hook-type and grip-type tilters turning the stock between passes. The finishing group, a compact cartridge stand with hydraulic gap adjustment and automatic gauge control, produces rails at up to 8 meters per second across 4 universal and 2 edging passes. Every finished rail is stamped with a unique number for full traceability before it reaches the cooling bed for controlled cambering and straightening. Supply chains aren't only about steel. They also include the branch lines that connect factories, ports, mines, and industrial sites to the main railway network. Building those connections often means upgrading active routes, installing new junctions, and coordinating track, signaling, and civil works without interrupting daily operations. Mass production is one side of the equation. The other is the workforce that has to keep building, fixing, and connecting it every day. Steel doesn't move itself. Before raw materials reach factories and finished products leave them, rail freight keeps industry connected. Much of modern industry depends on that unseen flow. Thousands of tons of material move every day without most people ever noticing. Crews inspect locomotives, couple wagons, and complete brake tests before departure. A central control desk tracks train movements in real time and maintains radio contact with drivers throughout the journey. The hard problem isn't building new. It's building new while the old keeps running. In Toulouse, crews extended a tram stabling yard while the depot stayed open. 6 tracks and 2 switches went in without dropping power. For China, the lesson is larger. Expansion cannot pause the network in use. Some networks aren't built once. They get rebuilt across decades. About 95% of a French city's tram network has been constructed by a single specialist contractor over 30 years. New extensions include joint immersion weeks, where the city's own maintenance crews train alongside contractor teams on track and overhead line work. How do you rebuild a national-scale station without shutting it down for years on end? A contractor lays out the method. A track-laying train drops concrete sleepers at fixed spacing, rail threads through the central groove, and clips down. A larger renewal train repeats the job at higher throughput. A heavy rail crane drops pre-assembled turnouts straight into the gap. The point is using the narrow window when nothing must run overhead. A flash butt welder fuses joints overnight, and a tamper packs ballast under each sleeper. In China, this window discipline matters because delays ripple across a countrywide daily timetable. Finding problems before they find you is the whole game. China and other countries' railways all depend on finding tiny faults early. In Wuhan, 2 inspection robots check bullet train undercarriages during the Spring Festival rush. Sensing, machine vision, and AI cut a 4-mechanic 3-hour inspection down to a 3-mechanic 1.5-hour job. Tight spots the cobot arm can't reach still get manual eyes. The next layer isn't on the train, It's in the data behind it. Engineers on the Yinchuan-Xi'an high-speed line use building information modeling to lay out equipment spacing and avoid cross-interference between systems. A new auxiliary monitoring system at traction substations watches equipment status around the clock for maintenance reference. Aluminothermic welds are where rails most often crack. Detecting flaws inside them is where inspection lives. A UK-led EU project developed a clamp-on phased array ultrasonic probe to test the roughly 1.7 million aluminothermic welds on a national network. Digital records now replace manual checks that left behind no physical trail. Some problems don't get solved with inspection. They get solved by replacing whole kilometres of track in one window. A French high-output renewal train runs the full sequence in a single shutdown. Ballast cleaning strips out the contaminated bed first. Track substitution then lifts old rails and sleepers and drops fresh concrete sleepers in their place. Field aluminothermic welds join the new rail segments end to end. Discarded rails are gathered by crane. The whole point is finishing before the line reopens to traffic. Fresh ballast pours in, the track lifts under hydraulics, and mechanical tamping heads pack the bed solid underneath. A full zone of track can be rebuilt in one window if you commit the resources. At St. Cyr, a 72-hour shutdown put 40 machines and 200 workers on site to cut out old rail, regrade the bed, lay new sublayer, drop turnouts by crane, and tamp the ballast before reopening. When throughput is national, a maintenance base looks less like a depot and more like a small city. The Wuhan high-speed train maintenance base, the largest in central China, services over 100 sets per day. The site runs busiest after midnight when trains return for overhaul. A clean train isn't cosmetic. It's part of the daily checkup routine. A Chinese high-speed set collects bug strikes, grime, and dirt at 300 kilometers per hour every run. Each night, it returns home for a wash. The wash hall is 198 meters long. 2 main bays handle multi-section and single-section sets. A 2-meter-wide control panel oversees the cycle. The cleaning works like a tunnel car wash, except the vehicle is 10 city buses long. A red laser detector triggers, brushes, and nozzles. A hot air curtain melts ice and snow off first, important on winter routes where cold water cracks the paint. Pre-rinse uses warm water. A neutral shampoo follows. For heavily soiled sets, alkali content rises. Calcium removal jets rinse the detergent off, then nozzles and brushes scrub the body. Soft, water-resistant bristles keep the paint intact. A 3.8 meter brush handles sides. A 1.7 meter brush handles the underbelly. Washing one 211 meter 8-car set uses 2.1 tons of water, fully recycled. Cycle time runs about 20 minutes. The bullet nose still gets a hand wash by humans because no machine reaches that geometry. At some point, a railway stops being only infrastructure. It becomes part of the city and industry that grow around it. From metro lines passing through apartment blocks to high-speed tunnels beneath entire cities, viaducts rising above traffic, and rail systems rebuilt while running, China's railway system no longer adapts to the city, it actively reshapes it. That is how China ended up where it is now. Material supply, contractors, machine fleets, inspection systems, maintenance bases, nightly wash cycles, all of it built around the assumption that the network keeps growing and keeps running. The trade-off doesn't get talked about openly, very often outside China itself. 50,000 kilometers of high-speed track came with massive long-term debt, mixed ridership numbers on smaller branches, and open questions about whether the model can transfer anywhere outside China at all. Thanks for watching. Stick around. The next video covers a job that sounds impossible until you see how. We'll see you there. Take care.